Okay, so for this problem, we're finding the area and volume set between various curves and lines. Pretty simple, but one of the first things you want to do is define your parameters. So for part A, we're working between y equals 1, y equals 3x squared, and the y-axis. From there, you're looking for area, so you should set up your differential. And for Cartesian 2D coordinates, it's really, really simple. Hopefully you guys all know this. Length times width equals area. So once you set this up, your next step will have to be to integrate it. But we're going to have to find our boundaries of integration. So we know that we're trapped for this area right here between this y curve and y equals 1. So that's pretty simple. On the low end, it's going to be 3x squared is less than our y, which is less than y equals 1. For x, we're going to be working from x is 0 to this point right here, which if we plug into this equation, if you plug in y equals 1, you're going to get left with root 3 over 3. So 0 is less than x, which is less than root 3 over 3. And then you're simply going to solve this integration. I will say for these interviews, doing the math itself is not necessarily what they're looking for. Obviously, you still have to be able to solve an integral, and I think this is an important skill to have. But the most important thing that you are going to be telling them is the setup to this problem, i.e. the sense that you understand that integrating will give you the area of a curve, and that you can manipulate boundaries to find those exact integrals that you're trying to look for. So this was the important part of this problem. And we're going to go through and keep doing them. Okay, so I solved the integral, and you get the resultant area of 2 root 3 over 9. I try to be explicit when I do my integrals. The more steps you show, the easier it is to catch your own mistakes, but also your interview will be able to see your thought process, which is, again, the most important part of these problems. So if we go on part B, we're going to go through the same thing, except our boundaries are now the x equals 1 line, the x equals 2 line, the same curve, and the x-axis. So we're working with x equals 1, x equals 2, x-axis, and y equals 3, x squared. So we're finding the area once more. So we're going from not x equals 0, but x equals 1 to x equals 2, which is pretty simple. And then our y's, we're going from 0 all the way now to our curve being the top of our area. And the setup's going to be the exact same. Your differential, you have our limits of integration. You're going to solve. So once you set up your integral, you're going to solve your integral. And again, it's a really simple problem. It's very similar style math. You get a resultant area of a equals 7. All right, so for part C, it gets a little bit trickier. We're now taking the curve we were working with in part A, and we're going to revolve it around your x-axis. You're going to find a volume. The process doesn't actually get that more complicated, but we're going to set it up in the same way. Starting by defining those boundaries. Again, we're using y equals 1, y equals 3x squared, and the y-axis as our boundaries. And then we're going to rotate around the x-axis. And again, you'll notice I don't have the x-axis labeled x-axis, and we'll talk about it in a second. So the first thing we're going to do is we're going to try to figure out what we're going to use for our differential. And this is where things get a little bit more complicated, but not too bad at all. So a volume differential is, again, you guys can probably intuit this. Length times width times height, that's the volume, but it's not the easiest way to solve this problem. The volume differential for cylindrical coordinates is going to be rho times d rho, d theta, dz. And then we can also, we're not going to, but you can also use spherical coordinates, which is r squared sine phi dr d theta and d phi. So these are all different systems that we can use. And even though our original boundaries are given to us in Cartesian coordinates, it's best to use a cylindrical system. And in this situation, I'm defining the x-axis as z, or height of our cylinder, y-axis is rho, or the width of our cylinder, and then obviously theta is just going to be our rotation. And then we're solving now a triple integral. Our next step is to define those limits of integration. So for theta, it's really simple. We're going from 0 to 2 pi. We're going all the way around. For z, our z, which is our x-axis, is going to be the exact same as before. We're going to root 3 over 3. And then our y integration is again going to be, it's going to be 3 x squared all the way to 1. But now we're using different coordinate systems, so it has to be noted that x goes to z and y goes to rho. And these are going to be our limits of integration, and this stays the same. All right, now we'll set up our integral. Volume, triple integral. We have rho, d rho, dz, d theta, 2 pi, and then we're going to go ahead and solve this integral. Okay, so once you go ahead and solve that integral, you're going to get a result of 4 pi times root 3 over 15. Again, the integral solving itself isn't what they're looking for. You do need to be able to solve that integral, so if you can't, please practice those. But the important part is the setup, and that you can find the limits of integration, and that you understand how to find that volume by rotating around the axis. Part D is the exact same thing, except we're going to rotate around a different axis this time. We are doing, again, y equals 1, y equals 3x squared, and now we're in the y-axis. We're going to rotate around that y-axis as well. We're going to use the same differential. Volume equals the integral of rho, d rho, dc, d theta. In this situation, my y-axis has become z, and my x-axis has become rho. So if we want to define our limits of integration, theta is going from 0 to 2 pi again. That will never change. Our rho is going from 0 to root 3 over 3, and our z-axis is going from 3 rho squared to 1. And we're going to set the integral one more time and solve it one more time. Okay, so once you solve the integral, you should get pi over 6. And again, this is the end of the problem, but what I want to highlight, the important parts of this problem are being able to identify what differentials you're going to be using, defining your limits of integration, and then expressing that you understand how to find a volume or an area based on the curves that you're given to the instructor. If you cannot do the triple integral, that is a problem. So please reach out if you want to go over solving integrals in general. But that is the scope of this first problem. Thank you.